All right, in the first video, we defined continuity. We checked all three conditions of being continuous at a point. And we defined the continuity on an open interval. And now we're going to talk about one-sided limits and therefore continuity on a closed interval. Let's hit the road. Let me just give you the definition of one-sided limits. We have two kinds. One is limit from the right and the other kind is the limit from the left. Let's say like you have a function f and the point of consideration is x equals c. When I say like the limit from the right, what I mean by that is that x's are chosen in a way that those sample points are chosen in a way that they are going to be on the right of c. So in other words, I'm going to walk on the curve on the right hand side of c, and I don't care what's going on in this side of the graph. All I care about is like how this how the walking on the curve in this side of the curve takes me to. So is there any limit value that I approach to? And there's a special notation for that. We use the we just say like limit of f as x approaches c from the right. So I use c superscript plus to denote the right the limit from the right. Okay, so let me just rewrite that. Okay, and we say like this limit is L. That means all of these guys approach the value L, which is right here. Okay, and there's the similar concept for the limit from the left. And this time here is the point of consideration, that's x equals c. And I'm interested in x's on the left of c. So I'm going in this direction, so I'm going in this direction on the curve. And I do not care about what's going on the other side of the graph. So all I'm checking is if the function values approach a specific value. And in this case, the limit value is, as you see, L. So, and then we use a specific notation for that. I use the minus notation as in the superscript here. So C minus. When you see this notation, you will read this as like limit of f as x approaches c from the left is L. And why do we need one-sided limits? There's a specific example for that. I can tell you that if you are working with radical functions, and especially the root here is an even integer, so then uh, you need one-sided limits because this function here nth root of x is not even defined for negative x values. So it's meaningless to look at the limit of this function as x approaches 0 from the left because for those x's this function is not going to be defined. So even in this particular case here, that I can only look at the limit as x approaches 0 from the right, and that's in fact 0. Okay. There's another cool example here that f of x equals radical 4 minus x squared. So we know that the radical functions are defined whenever the inside of that is non-negative. So that makes x's to be in between -2 and 2 in the domain. So outside of that, the function is not defined. Okay, outside of this interval -2 and 2, this function is not defined. So if you look at the limit as x approaches -2 from the right, as you see that I'm approaching -2 from right to left, as you see. And I'm walking down on the curve in this direction, so I'm getting to 0, and for that reason this limit is equal to 0. And if somebody writes here that what is the limit of the same function as x approaches -2 from the left, well, this doesn't exist because it's meaningless here because this function is not even defined for x's on the left of -2. Another cool application of one-sided limits is step functions, and one common type of that is called the greatest integer function. We have a special notation of that. We use this notation to denote the greatest integer function, and it's defined as the greatest integer n such that n is less than or equal to x. Essentially, we're just rounding the number down to the closest integer. So for example, the greatest integer of 2.5 is 2 because we're rounding it down to 2, and same as here, so the greatest integer negative 2.5 is negative 3 because you again round it down. And here's the graph of the greatest integer function. It's like a floor-looking type function, and this function has one-sided limits to be considered at the integers, right? Because at every integer value, the left limit is totally different from the right limit. For example, at x equals 1, the function values approach 1, but on the left, the function values approach 0. And this type of situation happens all the way at every integer value. The one-sided limit concept brings up the definition of the existence of a limit. So if you're looking at the limit of the function f at point C, and the limit exists, and if it's equal to L, if and only if the left and the right limits, let me just zoom in, as long as the left limit is equal to the right limit. So essentially all we're going to do for the existence of limit is checking left and right limits. If they're equal, we call that limit value is in fact the limit of the function at x equals c. In other words, I can perfectly write down here that limit of f as x approaches c as well is equal to L. So after all, we can talk about the definition of continuity on a closed interval. Let's say like f is continuous on the closed interval a and b. Whenever f is continuous on the open interval a and b, we know how to check that. As well, the sided limits, essentially at a, it's on the right, and b, it's on the left. They should exist, and they should be equal to the function values attained at the end points. So all we're going to do to check the continuity on the closed interval is the continuity on the open interval. And for the end points, we're going to check those sided limits. And therefore, the function is continuous from the right at A and continuous from the left at B. Okay, so essentially, as you see that this function is continuous all the way because I started graphing it all the way from point A to point B, but for point A and point B, we have to check all two conditions, and that requires you to check the sided limits. I'm going to close this video with an example. Let's say like we have the function f of x equals radical 1 minus x squared. And we do know that the domain of this function is the closed interval negative 1 and 1, because if you're outside that domain, this function is not going to be defined because you're talking about the radical of negative numbers. So for all points in the open interval negative 1 and 1, continuity of f follows from the earlier results that we proved. First of all, radical functions are always continuous as long as you're in the domain of the function. And this one just tells us that if you're talking about the limit of a composite function, especially the composition is on f and g, if they're specifically continuous, then you're talking about the continuity of the composite function. And this function is composed of radical x and the polynomial 1 minus x squared. So essentially this function is continuous on the open interval negative 1 and 1. So the question is like, what is going on at the end points? And at the end points, remember that we're going to check sided limits. And on the left end, it's the right limit, and on the right end, it's the left limit. And even graph-wise, we can check those limits. If you're on the right of negative 1, so that means you're going in this direction and getting closer and closer to negative 1. That means I'm walking down on the circle here, and the limit point, obviously, is equal to 0. And this is, in fact, the value of the function at negative 1. So that's good. That condition is satisfied. And if you're looking at the limit of the function as x approaches 1 from the left, that means I'm approaching 1 in this direction. So I'm walking down in this direction on the circle, and then I'm going all the way to 0, which is in fact the function's value at x equals 1. So we have the continuity on the open interval negative 1 and 1, and continuity, one-sided limits exist, and continuity, therefore, at the endpoints in my pocket. So the conclusion here is that f is continuous on the closed interval negative 1 and 1. And with this example, we've finished the discussion about one-sided limits and the continuity on a closed interval. So the next video is going to be using properties of continuity. Please watch next video. Bye.